Hello, everyone, and this is Álvaro speaking from RatedPower, and welcome to the webinar where we're going to talk about optimizing PV plants for seamless grid integration, and of course, how our software will help you achieving that seamless grid integration. We're going to give a couple minutes to see if everyone else joins. In the meanwhile, I wanted to, sorry. Yeah, I wanted to tell you about the event we host in Madrid, okay, with all the energy expert of the industry coming. The event is hosted in the wonderful Colegio de Arquitectos of Madrid, and it will be days 3 and 4 of April. And yeah, if you get your ticket before the 10th of February, you'll get a 50% discount. So go and get it because everyone will be there. Good. So let's still give a couple seconds to see if someone else joins, and then we'll start. Okay, I think we can get started. So as I was saying, we are going to talk about optimizing PV plants for seamless grid integration. As some of you may know, our software is a tool to simulate to very rapidly simulate PV plants and get all the documentation, and everything is very automatized. So today we're going to see how not only automatize, but I'm going to show you how to optimize that design in order to integrate it to the grid with based on the grid requirements. Um, First of all, a little bit about me. Okay, I'm technical advisor for the company. I work mostly for the Latin region, although I'm helping clients all around the world, and together with all my colleagues from the customer success team. Mm, And this is going to be the index for today. Okay, we're going to give a little introduction to the theme, and then we're going to see three important aspects that are the importance of switching and breaking stations, SVS, how to reduce the losses, uh, important for this grid integration, of course, how to size our equipment. Then we'll go to the software to see how we do all this, and a little recap to see all the steps we've been doing. Okay, so let's jump into it with the intro. Grid requirements. Okay, we're gonna basically define the grid requirements in three different aspects. First, the grid compliance. We're gonna ensure our plant meet all the regulatory and technical standards for safe and efficient operation within the grid. Of course, important. Secondly, we're gonna talk about the TSO requirements, okay, the transmission system operator requirements. Specifically, we're going to talk about the voltage control and frequency regulation. And the third one will be to minimize the electrical losses. Okay, we're going to see how optimizing the plant's layout and components to reduce energy losses and maximize efficiency from generation to delivery. So we basically sum this optimizing PV plan for seamless grid integration in these three different aspects, and these three aspects take us to the 3 points that we are going to optimize. Okay, so based on the grid requirements, there is a need to ensure at the point of interconnection three things. The voltage, okay, so you will get a point of interconnection in a substation and at a voltage level, and it's important that you arrive at the substation at that voltage level. Also, the active power you have by contract and the power factor that may be important, okay? For this third last point today, I'm not going to get very technical and it's not going to be a lot of theory. But I wanted to tell you that we hosted a couple months ago this webinar that was a very big success about grid integration studies, more technical about this power factor, and I very much recommend you to watch it. We're going to send you, okay, after the webinar, all this information. And yeah, here you have the link. So let's start early with the importance of switching and breaking stage. So what's a switching and breaking station? Basically, it's a interconnection facility that allows us to gather all the different MV lines that are in the PV plant. You know that there might be a lot of different lines gathering all the energy from different power stations. And instead of having all these lines going all the way to the substation, we have now the possibility to have this switching and breaking station in our PV plant and then going in the same voltage level, because maybe there is no need to increase the voltage, to the final point of interconnection, okay? This way, we, of course, reduce MV cables, we reduce the necessary materials, so money, we reduce the losses and unnecessary voltage levels. When we talk about this, it's important to talk about the flexible interconnection schema. This that you're seeing right now is what we always had in rated power, is what we now call level one. So we always had this, of course, at a low voltage level, the modules that go to the power stations, and then in a medium voltage level, go to the substation where the voltage is increased, and you can draw an overhead line to the grid point or not. That's your decision. And we could have, we always have the option to do the same with a switching and breaking station, okay? Gathering MV lines and going to the point of interconnection. So what we now have is a level two, which is also the possibility of having first switching and breaking station and a substation, then going with an MV cable, underground MV cable to a substation, and then increase the voltage. And with that overhead line, you can go to the point of interconnection after this. And we also did a third level. It's a more technical level. Okay, it's a different one. People use it more if they have different, for example, different blocks of PVs stuff. But today we'll be focusing, of course, in level number two, okay, of having the possibility of have a switching and breaking station, then MV line till the substation, increase the voltage, and then go with an overhead line till the point of interconnection. Also, we'll be sending you information about this, as it might be a little bit difficult right now, okay? So with this, we are ensuring the voltage level at the point of interconnection with the most optimized option, okay? We could even check all different options, see losses, cost, stuff, and then decide. Second point, reduce losses, okay? So first of all, we'll need to see where do we define losses in rated power. Okay, we define losses in mainly in 5 different points, okay? Every time we have a transformer, so in the power station transformer, substation transformer, and PCS transformer, also at the inverter level, but that is depending on the inverter, okay? So it's always based on the inverter OND. And then at the PV plant losses and the PV module losses. Here at the right, we have 2 examples of different screenshots from the software where we see how we define the substation transformer losses here in the one in the right, and the one in the left, sorry, and the one in the right, we see the PV module losses. Okay, these are parameters that are by default or based on the module PAM file. Okay, so with all this taken into account, what we're gonna see later is this monthly breakdown, for example, and we can, while we design, we can always see these losses as we see in the image on the right, okay, the big one. You see the different losses, the front face of the model losses, back face, electrical system losses, and the results, okay? And what we have added lately is first the power that we have installed, okay? For example, the rated power will be the sum of the power of all the models, but of all the inverters, sorry. But then we run the power flow analysis, and we can give you also the active power at the point of interconnection, okay? Taking into account all these losses. Once you see this, you can see if you are delivering to the point of interconnection the power that you had by contract, more or less. What can we do with that after that point? Okay, we can check the active power delivered at the point of interconnection, and we can check two things. First of all, we have the option of simulating with a maximum capacity or a specific capacity. Okay, maximum capacity is you upload to the software an area for models, and the software is going to use the whole area to install models. Okay, so it's going to get the maximum possible capacity in that area with the electrical configuration that you set, of course. On the other hand, we have specific capacity is if in case you know exactly how how many megawatts you want to install, you set the amount of inverters as we have in the image in the right, and that's what we will try to install in the software. Okay. Once this is defined and you know the active power, the delivery point, you can see if you need to set an active power limit at the delivery point. If you do that, there is no way, like you will never you will never deliver more power than what you set at the active power limit. Okay, and in this way we will ensure the active power at the point of interconnection to comply with the contracted capacity. And the last point we'll be seeing today is equipment sizing. Okay, equipment sizing is something related to the power factor. Okay, this is where I said I don't want to get very technical, but some of you may know it already. Power factor is something important in especially in some countries where you need to get to the substation with some specific power factor, for example, 0.95, something like that. And what does this mean? As you know, when we talk about power, we have two different kind of power. We have active power and reactive power. The active power is the real power, what we can use and what we will get money for. But we need to also deliver a little reactive power. This is the classic example of the beer. Okay, so the whole beer will be power, and then the brown part of the beer, the liquid itself, will be the active power, and the reactive power will be all the foam. We don't want it, we don't like it, but we need to deliver it because there's also other charges that consume this reactive power. And how do we define this in the software? Easy. So we do a first estimation of inverters when we run the simulation. We design the PV plan, and then we will check if we are meeting the TSO requirements. If we are not meeting TSO requirements, we go back, we update inverters to the power factor, and we add capacitor banks if necessary. Why do I say if necessary? Because we have two different strategies. Here in the right, you have a screenshot from the software as well, okay, of how we set it, but we'll see it later, of course. We have these two strategies. First, inverters only strategy to compensate reactive power. We set the inverters based on the power factor needed at the point of measurement and add inverters to achieve the necessary power. It means we'll be telling the software the power factor we want to get at the point of measurement. And based on this, the software is going to set the inverters to that power factor. And it depends. If, for example, if we're in a maximum capacity and we cannot add more inverters, we might see our active power being reduced. If we are in a specific capacity, we might see that the software installed more inverters because it needs more inverters to get to the same level of active power. Okay. Second strategy will be using inverters and capacitor banks strategy to compensate reactive power. In this case, we can decide what part of the PV plant is going to be compensated by inverters and what other part is going to be compensated by capacitor banks. In the image in the right, we see that all the yellow part is using inverters from the PV plus storage system until the substation output, okay? And after the substation input, till the grid, we're going to compensate it with capacitor banks, okay? So we are not going to be modifying our PV plan. We're just going to have more costs, of course. And with this, we are ensuring the power factor required by the transmission system operator at the point of interconnection. Okay, so the fifth point is the demo. So what we are going to do is we're going to jump into the software and jump into RatedPower. So I had a project created, but we want to create it live. This is the project, okay, grid compliance. I don't have any designs yet, so we're going to start with a new PV design. And first thing I'm going to do is set my site, okay? So I'm going to use this first site. We have an available area with a restricted area because we have some kind of a path here. I want the string inverter. And then what I have is a MV line, okay, it's an underground line that goes all the way from the PV plant to the substation here, okay? So what we are going to do is set in the inverter, and I also want to go to grid point, and I want to say that I want my substation to increase the voltage from 20 kilovolts to 220, and I'm gonna run this first design, okay? I'm gonna already save it, and it's already up and running. We have rated power of 47 megawatts, active power, the point of interconnection of 45, so we are losing 2 megawatts in all this journey. And I'm gonna edit the name to design number 1. Good. So we don't really like this long MV line as we are having a lot of losses. I'm gonna try to have an overhead line. I have already here in this site prepared the second design, which is basically the same, but the substation is here next to the plant, okay, next to the PV plant. And then we have this overhead line all the way till the point of interconnection. And I'll just do the same and run the design. Design is running, same rated power at the PV plant. And we see that we got a little bit more, but not a lot. But this is how we are sure that we are having this 220 kilovolts here at the point of interconnection. I'm gonna save this design. And yeah, this is how we would use rated power, okay, to optimize this all this grid seamless integration. We can change also the name and call it design number 2, for example. And at this point, I like to imagine that we are required, because of environmental reasons, to not having this overhead line over this kind of forest. So I created this third site where we have a switching and breaking station next to the PV plant. Then we are having this medium voltage cable all the way to this substation. And then we have this overhead line till the point of interconnection. Okay, it's the same one. And we can run the design. Probably cost might increase. Here we have the capex sheet. Okay, we can change the capex sheet, for example, to this one that I prepared. And I can run the design again to have a more accurate costs. Good. So at this point, we have connection that we like, connection that we are good with. We are ensuring that we have 220 kilovolts at the point of interconnection. We are respecting these environmental restrictions. And then we have the overhead line, which we know that is a way of having less losses and a cheapest option. I'm going to save this one. And I'm going to edit it with number 3. Save. Okay. So once the voltage level is ensured, we're going to go to the next point, and is losses. I like to check different points. Today I'm going to go to the main ones. Okay, it's going to be in the layout, for example. Here in the energy, I can see the near Satan losses. In this case, for example, is 2.45%, and I would like to decrease that a little bit. And I want to imagine that I have by contract 38 megawatts at the point of interconnection, so I can lose some energy. I don't have some power, sorry. So I'm going to go to the distances here, and I'm going to set the pitch distance to 7. And I'll maybe go to energy and check, for example, in the model losses. This is not a very, like soiling losses here are not high, so I'm going to set it to 1% in the PV model losses. And in the PV plant losses, I have the plant auxiliary loss, PV plant availability, and grid availability. I'm going to set the PV plant availability to 99. And I'm going to run the design. This is our first design taking into account losses, okay? As we see, we are already losing a little bit of power, but we decrease the near shading, and we can save this design with design number 4. So we are delivering active power at the point of interconnection of 40 megawatts. What does it mean? It means we are still a couple of megawatts over what we have by contract. What can we do here? We could do two things. We could go to layout, to power requirements, and either change the maximum capacity to a specific capacity, but then if we have we will be sizing completely different our PV plan, okay? Because we'll be sizing by number of inverters, and if we were to have any issue, it will lead to not delivering the active power that we have by contract. So what I'm gonna do is allow this energy clipping, curtailment at the delivery point, active power limit of 38 megawatts, and I run the design. Here we're going to see the same result because the power flow analysis tells you what you could achieve at the point of interconnection, but in all the documentation we generate, in all the energy production documentation and stuff, we'll be seeing how the active power delivery point is never over 38 megawatts. Okay, so with this second point done, we can jump into the third requirement, that was the power factor. For the power factor, we'll be going to the grid point. Grid point for us is everything that is over after the power station, okay? The medium voltage, you can set it here with all the high level. And this, we can set it again to 220. For example, if we go to the overhead line, we can see there's a warning saying that the electrical criteria of the design might not be met. We suggest you increase the number of conductors per phase. Okay, I set it to 2. Warning is gone. And then we go to grid requirements. We are going to size using power factor requirements. Okay, cosine of phi. We click it, and as soon as we click it, the design completely changed, because even though we require power factor 1, it means that, for example, in this case, the resulting power factor at the inverter's output is 0.9872. So it's already changing, but I don't want 1. I'm gonna do it to 0.95. And not only this, but I also want to check the strategy. Okay, so I'm gonna be compensating all the reactive power before the substation, but not of the overhead line. But I want to take into account the overhead line as well. So you change the point of measurement, I click in done, and I run the design, okay? While the design is running, I'm gonna change the name of this one. As you can see, I can constantly check one design or another, and I'm gonna go back to the one that was running. We can already see some differences. Like for example, the LCOE increased a little bit. As you can see, number 5, we have an LCOE of 33.41. And the new design is 33.82, probably because we are using more inverters. I'm gonna edit the name to number 6, and you'll see later why I change all these names. So we have already sized the power plant, taking into account the power factor using only inverters. Now we're gonna see how it is if we use inverters and capacitor banks. So as we see, there is a new color here, okay? We already said 0.95 is the required power factor. And now if we jump into the strategy settings, we see that there is part that we can compensate with inverters, and this is the start of compensating using banks. I want to do not only this, but also for the MV path. I want to compensate with inverters only from the inverter level till the switching number station, and the rest with capacitor banks. Done, and run design again. And with this, we will have our seventh design, sorry. I'll save it. LCOE increased a little bit, no, decreased a little bit, sorry, because we are using less inverters now. I'm gonna edit the name and set it to 7. So now we have these 7 different designs, and if I go back to the project, I'm gonna see the 7 designs I created. For example, the first 3 are related to the lines. So if we click the 3 of them, we could compare them. We can compare stuff as the specific production. For example, we see how the first one is the highest, okay? 1, 2, and 3. The total price of number 3 is the highest as well. Okay, we could do like this and order them. First one is the cheapest, then second and 3. And we can filter what we are comparing, okay? Not only filtering, but yeah, we can. This is comparison of these 3 things, but we could go back and compare whatever. We can even compare all of them, or for example, the 2 last designs we did with. I can first also change the name here. I can add inverter, and here select inverter and capacitor bank. Okay, and I can compare them now. If we were to have, we could see if we had the maximum capacity at different volt power levels, for example. But in this case, what we can see is the specific production, different energy levels. LCO is changing, okay. The total price of the PV plant is changing. The inverter is higher than inverter and capacitor banks, probably because our capacity has different prices for inverters and capacitor banks, and equipment is changing constantly, okay? And yeah, so imagine we would stay with design number 21, we would already have a design, okay, where we are meeting all the TSO requirements. We feel like it's very optimized, and we're good to go. So what did we do exactly here, okay? Let's do a little recap. We did a first design where we run the simulation without limiting power or compensating power factor. At this point, we are not ensuring any of the 3 points mentioned, but we need to check that the PV plant will work. Okay, we need to check that the space we have is enough. We need to check that, yeah, the line is good and everything. First, then we'll do a flexible interconnection scheme optimization in order to get the voltage level that we want at the point of interconnection. We decided to add a switching and breaking station to reduce losses and gather all the MV lines in just one line, and an overhead line to secure power. In this case, we are now ensuring that the voltage level is the most, we are ensuring the voltage level in the most optimized way. Once this was done, we went to the losses study. Okay, we decided to increase the pitch distance and adjust a couple losses. With that adjust to the reality, we are still generating what we need. So we check the active power, and after making sure we generate more than enough, we need to limit it. Now we know that we'll never exceed the contracted power. And last point was the power factor compensation. The grid TSO require a power factor of 0.95 at the point of the connection. We tried two strategies and decided what's the best option. With all this done, we got a final design. Okay, with all that done, we have final design ensuring the voltage level, never exceeding the power contracted, and the power factor at the point of the connection. So thank you very much. And if you have any question, this is the moment. Okay. And I see that there are some already. Um, I hope you liked it and you enjoyed it. Let me see. Okay. We have here alert is saying that how is it going with getting the grid connection as cables in my area? All voltage levels below 400 shall be in cables as new overhead lines are not allowed. Mm, I don't think I really understand your question, alert. Sorry, but I'm just gonna show how would flexible schema work in this case. For example, here we have these two levels, okay? And if we clone the design, we can perfectly define the connection type, the high voltage level, okay? And it's I don't remember the minimum. I think it's just 46, but the maximum is 550. So you can always have it up to 400. If this is not exactly what you ask, please don't hesitate on reaching out, and we'll be happy to help. Okay. Mm, okay. There is another one. Can we store those clipping and curtailment losses in a base? Okay. I think what you mean is once in layout we define energy clipping. We have this curtailment delivery point, and there is some clipping losses. Of course, there is some clipping losses that we can perfectly see here. Okay, if we download the energy geo results, I just open it. There is one of the tabs that is going to show us all these clipping and curtailment losses. At the beginning is 0 because probably these first days of the year we are not generating more than 35. But as you can see here, as we approach to more to have more irradiance, yeah, we have here up to 3 megawatts, 3 megawatt stuff. Good. So the answer is yes. Okay, we RatedPower we can set a storage system. Okay, in this case it's not allowed because we didn't define an area, but we changed the equipment to central inverter. Now it is allowed, and we can, for example, set DC base in this case and run the design, and everything that is not going to the grid will be going to the storage. Okay. I see another question here from Felipe. He says, it is possible to establish the MB cable route or pre-design gives optimal route? This is a good question because I didn't want to jump in the site creation, but for example, here, the MB routes inside the PV plant is designed by RatedPower, okay? This is the most optimal route is designed by us, but the route from the switching and breaking station for the substation is, of course, something you can define. If we clone this is something I can completely manually edit. I can delete this one and I could add a new one, for example, the empty cable. If I wanted to leave our switching navigation here, go all the way here, here, and here, I'll just save it like this, save as a new site, and generate the design again. And this new MV route will be taken into account, okay? And will be taken into account for all the financial calculation, the losses, and everything. Okay, and someone here says, Javier says, I have seen you are always using maximum capacity. How would you use the specific capacity? Well, so as I explained, I have been using maximum capacity to be able to do designs easier. If I were to go to layout, power requirements, here I have the maximum capacity where we just set DC-AC ratio, either at the inverters or at the point of interconnection, and I run design. With a specific capacity, I am gonna go back to the string inverter. I will just have to set the number of inverters. For example, with these small inverters, I know I need at least like 240, for example. Yeah, this is levels that I'm happy with. I'm gonna go for 220 and even less, 210. So like this, I have an active power of 42. I can run the design, and this is a little bit more than what we had before. So we are not achieving this. Let's try with 200. Okay, so with 200 is 40.183. If I run the design, I'm going to see how the rated power here is exactly what I decided to install. Yeah, there we have it, okay? And this is how we work with specific capacity. When the tool is used for prospection, we always recommend to use the maximum capacity to see how much capacity you can store in a, you can generate in specific area and specific capacity if you already know how much you want to have. Okay, another question from Alert. Do you take the Q capacity into effect? Well, I think this one has been already answered. She says as there is requirements in the FG for Q capability that has to be available at the POC. This sometimes require additional inverters to deliver defined. Yeah, this is exactly what we said. Okay. Whenever in the grid point we enable the grid requirements, we will take all that into account. If you were to do the exercise of having a specific capacity with an amount with this not enabled, and then with this enabled, you'll see if you download this bill of quantities, how you will have more inverters 100%. Okay. If you have a specific capacity as if you have, sorry, a maximum capacity, as you said, probably the number of inverters is the same, but you'll have less active power, of course. And yeah, I think we are good. There's no more questions. So thank you very much for attending the webinar. I hope you learned about the tool and you liked it and you liked what we shared. And yeah, we hope to see you in the next one. Thank you so much.